Hi everyone. Today I want to tell you about a paper with Oded Goldreich on non-adaptive versus adaptive queries in the dense graph testing model. The plan is simple. I want to tell you the main result. It's a tight quadratic gap between adaptive and non-adaptive testers in this model. I want to explain the main tools we use, robustly self-ordered graphs, already initiated in a previous paper, and local self-ordering procedures for such graphs. And the main message is that these tools afford local and robust reductions aimed for property testing between ordered and unordered structures. So adaptive versus non-adaptive query algorithms. The setup is there is a huge object, maybe a function, a Boolean function or sequence F, and we want to understand something about it via queries. There are two types of algorithms, non-adaptive, in which we ask all queries in advance and get the value of these queries of F on all of them. Whereas non-adaptive algorithms are stronger. They can ask the first query, obtain the answer F of A1, use it to decide the second query, obtain the answer for it, etc. These are adaptive algorithms, and of course, the question is when and by how much does adaptivity help? This was studied in a variety of settings, decision trees, quantum algorithms, PCPs, Oracle machines, and I want to talk about this question in the setting of property testing. Everybody is familiar with the setup. You have a universe of objects with a metric or distance function on it, a subset P, which is a property you want to test, and a sort of complementary subset of F epsilon of everything which is epsilon far from this property. And a Q epsilon tester is a probabilistic algorithm that on any input from this universe makes Q queries. And if the object is in P, it should accept with high probability. If it's not, if it's far away from it, in F epsilon, it should reject with high probability. And if it's in this amorphic region, close to P, then we don't care what it does. This was studied on a variety of objects, sequences, functions, distributions, groups, dense graphs, sparse graphs, and for a variety of properties of these objects. We want to focus on dense graphs and on this question of the relative power of adaptivity versus non-adaptivity. So our universe is graphs. Our property is a graph property, namely close under isomorphism. And in the setting, comparing this relative power, let's fix an epsilon, maybe some constant like 1%, and define QA of P and Qn of P, respectively, the minimum number of queries required by adaptive testers and by non-adaptive testers. And maybe surprisingly, Alon et al., and then more precisely, Goldreich and Wigderson, showed that the gap is at most quadratic. It, of course, can be exponential in some settings, but here it's at most quadratic, namely, any adaptive algorithm with Q queries can be simulated by a non-adaptive one with at most Q squared queries. And the question since then was, how tight is this upper bound? Can it be improved or is it tight? An important result was obtained by Gonen and Ron a decade later, showing that there is a gap. It's at least power 3/2, so somewhere in the middle between 1 and 2. And our main result is that actually the original upper bound is tight. There are properties for which non-adaptive algorithms require quadratically many queries as adaptive ones. In this result and the previous one, I'm ignoring polylogarithmic factors. The important thing is the way the proof is obtained is used by reductions to property testing bounds in the case of ordered structures like sequences. So some are moving between this unordered case, which is difficult, to an easier one. And how we do it is what I'll explain next. We do it, so let me talk about ordered and unordered structures. Order, of course, is very important. So sequences are prototypical ordered structures. We may have these two words. Of course, they are different, and the reason they are different is because the coordinate of letters, which letter is where, is important in words. This is different when we talk about unordered structures like graphs. Here are two objects again, graphs. They look different, but do we want to count them as different? Of course, not really. If this is a particular labeling, we can label the other graph in this way, and then we see that they are actually the same graph. So here the right notion of equivalence is isomorphism. This leads to explaining the important notion of asymmetric graphs and the distinction from symmetric graphs. So here's a pentagon again with a particular labeling and the edge set that comes with this particular labeling. And here's the same graph again. We say that a permutation of the vertex names is an automorphism if it preserves the edge set. So let's look at this example. Of course, the identity will always preserve the edge set because it doesn't move anything. But in this example, there are more automorphisms. For example, if we still shift the labels, or if we take reflection, we still get the same labeled graph. So this graph has symmetry. And the question is, here are these non-trivial symmetries. An asymmetric graph is one which does not have any non-trivial symmetry, no non-trivial automorphism. In other words, if you move, at least if your permutation pi moves at least one vertex, then it must move at least one edge. Again, here's the definition. For if your permutation moves one vertex, it must move an edge. Here are some examples of, the smallest asymmetric graphs have 6 vertices, and here are all of them. If you want regular graphs, which are more interesting, then the smallest has 12 vertices. This is the smallest one, it's cubic. It's not hard to see, counting the argument, that most irregular graphs for any D are asymmetric, so they are abundant, but constructing them is not so easy, and we'll do even more than that. Okay, so here are some equivalent definitions. For example, a graph is asymmetric if whenever you get an isomorphic copy of it, again, a labeled graph, there's a unique way, a unique permutation that will preserve the edge set. So you can relabel the vertices using pi so as to get the original edge set. An equivalent one is that asymmetric graphs have really a unique labeling of their vertices. They can be uniquely named. For example, there are many ways to do it. For example, since all adjacency matrices of these isomorphic graphs of an asymmetric one will be different, the lexicographic first it serves as a good labeling, for example. So here I found to show you some labeling. This is why we call asymmetric graphs also self-ordered graphs. They can order themselves. Of course, how to find this ordering is a very important question that we will deal with soon. But first, why are they good? Well, they are good because they afford these reductions between ordered and unordered structures. If you have these two words we saw before, these are ordered structures, we can embed them into graphs if we have an asymmetric graph. Simply put these letters according to the canonical labeling. And of course, once we have these now labeled graphs, they will also be different. In fact, they will be non-isomorphic. It doesn't matter if you rotate this, you can still obtain the canonical ordering and see that the labeled graphs are different. You don't have to consider labels. You can replace labels by gadgets. For example, if the letters, the alphabet was binary, we can either put or not put a self loop around the vertex according to whether the bit was 0 or 1. Okay. These are the reductions between ordered and unordered structures, and they were already known and used in logic and descriptive complexity. These settings are, self-ordered graphs are good because you have complete access in general in these applications. You have complete access to the full graph. But we want to look at situations where you only have sampling access to the graph, like we have in property testing or statistical applications. And for this, we are going to introduce robustly self-ordered graphs as follows. This was done in our previous paper. Again, here's the definition of a self-ordered graph. If you move at least one vertex, then you move at least one edge, right? And it's robustly self-ordered if for any fraction alpha, if you move an alpha fraction of the vertices, you must move at least an alpha fraction of all edges. Okay, alpha can be any fraction, also depending on the graph size. So in a way, RSO graphs are as far from being symmetric as possible. Of course, you cannot hope for more than this. And these are the graphs we want. Can one construct them? Do they exist? Well, existence is not hard like asymmetric graphs. You can, counting argument reveals that most irregular graphs are RSO. Constructing them is a different story, and that was the main result in the previous paper. We constructed them both in the sparse case and in the dense case. We had several constructions that are different between the different parameter regimes and employ in the constructions some complex other pseudo-random objects. I unfortunately have no time to talk about this. I just want to stress that these are strongly explicit constructions in that adjacencies or incidences can be determined in polylogarithmic time. That's, of course, very important for the application. It's not enough to have robust self-ordering. We also need to find this ordering locally. So what is exactly that? We fix an RSO graph with some fixed vertex names. And the problem is the following. Somebody gives us an isomorphic copy using some permutation sigma. And the task is to find this unique isomorphism. And remember, we get only local access to the graph G prime, just can sample vertices in neighborhoods. And we develop such self-order algorithms. They are called LSO, local self-ordering algorithms. Specifically, we construct explicit deregular RSO graphs which have such a procedure, which specifically is the following. Given oracle access to any such graph G prime and any vertex in it, we can compute both sigma and sigma inverse of I in polylogarithmic time. That's a local self-ordering procedure. It can be done for any particular vertex. We don't need to look at the whole graph. This was done for sparse graphs in the previous paper, and here is part of the main theorem, doing it for dense graphs. And having these tools, the reduction sort of suggests itself. I'll tell you the template, the detail can be complex. But basically, you start from a property of unordered structures, like sequences, binary sequences of length n. You fix one of these graphs, RSO graphs that has a local self-ordering procedure, and embed the sequence in it, simply labeling every vertex with a bit sitting on this coordinate. So let's say add or not add a self-loop. And then we get graphs, and the graphs this property, new property P prime we define in the world of graphs are all isomorphic copies of these graphs G sub x. And of course, the main thing that enables the reductions are all the properties that I described. The locality of the embedding, of course, means that we can obtain the bit from looking just at the neighbors of I. Robust self-ordering ensures that distance is preserved. So the distance between x, any x, and the original property is roughly the same up to constants as the distance of any isomorphic copy of G sub x to the new graph property. And the local self-ordering is used, well, computing the sigma in one direction helps for upper bounds and the other for lower bounds. And of course, both are important if you want to put, let's say, a gap between adaptive and non-adaptive algorithms. We need both upper and lower bounds. Concluding main points, we define a new pseudo-random notion with RSO graphs. We have explicit constructions for them in the dense and sparse case. And in fact, these graphs also admit efficient local self-ordering procedures, and using them, we get these applications, some in the previous paper, and here this quadratic gap between adaptive and non-adaptive testers. There's some interesting follow-ups. Oded has a paper relating these notions. Of course, we need both, but the question is, if you have one, do you automatically have the other? Very interesting paper. Also, as a follow-up of one of our construction, follow error cloaking codes, which are permutation codes. And yeah, I expect more to follow. Thank you very much.